Okay, in this video we'll be talking about the derivatives of exponential and logarithmic functions. If you recall from previous years and from previous chapters, exponential functions are any functions where the variable is in the power, is in the exponent, okay? The base is always a constant in an exponential function. This example this section will only deal with exponential functions where the base is the number e, the natural number. So you will not see questions like this where it says find the derivative of this. Okay, for the purposes of this course, we will not be doing this. Okay, so only functions where we have the base with the number e. Okay. For the logarithmic functions, when we're looking at the derivatives of the log functions, we will only be looking at the derivatives where we have the natural log, where the log is in base e. Okay, this is really the same as log base e, right? Okay, so log base e of x. So this will be the only case that we'll be looking at, only type of logarithmic function that we'll be looking at. All right, so let's do a little bit of review here. The exponential function looks like this, right? Where we have it's always going to be positive because any number that I put into x will result in f of x being positive. And if I put 0, I will always end up with it passing through the point 0, 1. I'll get an output of 1, okay? And it exponentially grows as my x increases. The log function is the inverse. The natural log of x is the inverse of e to the x. Okay? And you can see that the graph will look like this. Remember that the inverse goes across the line y equals x. Okay? It's reflected across the line y equals x, where the reflection is the inverse of the function. Okay, so this would be e to the x, and this would be ln of x. All right. Also note that when we talk about the log function, the domain of a logarithmic function must always be positive. Okay, the inside part here must always be positive. Okay, because it doesn't exist. The values of this will not exist over here. It's undefined. Okay. And so when we look at the derivative of e to the x, okay, I'm just going to give you the derivatives, and we won't go into the proofs, but if you're interested in finding out why the derivatives are the way they are, you can look them up online or in your textbook. All right? F prime of x is e to the x, okay, which is really nice. If f of x is e to the x, the derivative of this is itself. Okay, if I were to take a look at all the slopes of these lines here, of the tangent lines, I would find that the way that those slopes are changing will follow the pattern of e to the x. Okay, and that shape will result in the same graph as the original, which is very interesting, but that's just a rule to keep in mind. Okay, if f of x is the natural log of x, the derivative turns out to be 1 over x. Okay, so 1 over x looks like this. And since 1 over x, this is just a note here. Since my original domain was x is greater than 0, the domain of this guy must also be, at most, the same domain as my original function. Okay, so what that means is even though 1 over x looks like this, since I'm only interested in values that are greater than 0, this part actually doesn't matter. Okay, so I'm going to ignore this, and so I would only be looking at this graph right here. Okay, so this would be 1 over x. So just to kind of summarize this, if I have the derivative, if I have y equals e to the x, the derivative is e to the x. Same thing, which is really nice. It's very easy. Okay. Now, the only time this might become a little bit more complicated is if instead of x here, I end up with some function of x. So, for instance, this was like x squared plus 2. If that was x squared plus 2, then we would say that's a function. And so if I take the derivative of that, I end up with e to the f of x. I keep the same expression here, and I multiply it by the derivative of my function. So this is an example where the chain rule has been applied to y equals f of x. Okay? Y equals natural log of x. That the derivative of that function becomes y prime equals 1 over x. If I have y equals the natural log of a function, where instead of just a nice x here, I have some expression in terms of x, then the derivative of this whole thing becomes 1 over f of x instead of an x. Okay, so 1 over the original inside times the derivative of the inside. Okay, so that's the chain rule being applied here. All right, so just notice the pattern. E to the x here looks similar to e to the f of x, and 1 over x here looks like 1 over f of x. Okay, so that's when we apply the chain rule. Okay, so let's try some examples here. Y equals 2 e to the x plus e to the minus 3x. Okay, so you can see here that I have, let's see, I have an e to the x and I have an e to the f of x. Okay, and they're separated by a plus, so I'm going to take the derivative of this separately and just add those two. Okay, and that's what I do. Since 2 is a constant, that doesn't change when I derive this term. So I end up with 2 times e to the x, since the derivative of e to the x is e to the x, plus e to the minus 3x. So this part stays the same when I go down. Okay, and then I do the chain rule, so times the derivative of the f of x, the mini f of x here, which is minus 3. And then I simplify and I get this expression. Okay? All right. Here's another example. Y equals x squared times e to the x. Okay, so now I have e to the x, which is one function, and I have x squared, which is another function. So I really have two functions here being multiplied together. Okay? I have one function here, one function here. Let's call this u and let's call this v. Okay? And now we can use our product rule. Okay? So I take the derivative of the first function, and here's our product rule over here. I take the derivative of the first function, so that becomes x squared becomes 2x, times the original function of the original second function, which is e to the minus x, plus, right, the product rule says plus, and then I do the inverse, or I do the flip, the opposite. The derivative of the second function, which is e to the minus x times, and since this is not just an x, I have to use the chain rule, and I end up with times negative 1 times x squared, the original first function. So there's my derivative, and I can now simplify that, okay, into this. All right, let's look at one more in this example. Y equals 2 to the x over x. Well, that's really, if you look carefully, you'll notice that there's a top function and there's a bottom function, okay? So I could probably use the quotient rule. Do I have to use the quotient rule? No, I could probably use the product rule by making this x to the negative 1. But let's just try it with the quotient rule, because you're going to need to practice that anyway. All right. So the quotient rule says u over v prime, quantity prime, is the same as, and I like to remember it with the v, the denominator, becoming squared. Okay, so it's the original denominator squared, and I like to put the denominator in the front, so I put v and v here, v times, and then I do the opposite, u prime minus v prime u. Okay, and I flip those. Remember that this is a minus, not a plus. So x v times u prime, okay, well, let's say that's u and that's v, okay, and there's my v prime minus v prime, which is 1 times u all over v squared, which is x squared, okay, and then I simplify that, and I end up with 2x e to the 2x minus e to the 2x all over x squared. I can factor out this term here, so I factor it out, and there's my answer. Okay, let's do one more example with finding the gradient function. Okay, what's the gradient function of f of x? Well, the gradient function is really just f prime of x, okay? So I'm still doing the same thing, just using different words. Here's my function. Now this time, we're actually going to be using the chain rule, okay? Because we have the outside function is kind of like u, okay? And my inside function is kind of like this, okay? So I guess I could say u is equal to x squared rather than u, okay? So there's my outside function. So I take the derivative of my outside 3 times my original squared, because that's the power rule, times the derivative of the inside, which is e to the x, and I simplify to get that, okay? For part B, it says f of x is 1 over the square root of 2 e to the minus x plus 1. I can rewrite this so that it's in a power, a single power, and then I can apply the chain rule. This is the same problem as this, basically. And I end up with minus 1/2 times the original to the minus 1/2 minus 1, which is minus 3 over 2, times the derivative of the inside. So this is where it gets a little bit tricky. I'm applying, to find the derivative of the inside, I'm going to need to use the constant multiple rule and the chain rule, okay? So the derivative of 2e to the minus x plus 1, that goes to 0. That's why there's nothing here. And then 2 just stays the same, and I end up with e to the minus x. That's the derivative times the inside, okay? So there's multiple steps going on here. We're applying the chain rule really to this guy and to this guy. So we're really doing the chain rule twice, okay? And then I simplify that to get this expression. All right? Okay, now let's move on to log functions and their derivatives. Remember we said that the derivative of y when it's ln of x is 1 over x. The derivative of ln of f of x is 1 over the original inside times the derivative of the of f of x, okay? So find the derivatives of the following. Y equals ln of kx. Now, this is a function, isn't it? Okay, it's not just a normal x, so I write 1 over kx times the derivative of that, which is k. And it turns out that the k's will cancel, and I'm left with 1 over x. Okay, so that's kind of interesting. If I have the natural log of k to the x, and I take the derivative of that, the derivative of this, okay, and I'm going to use this, is the same as the derivative of ln of x, okay? And just to show you why that is, well, what's ln of kx? Ln of kx is actually going to be, if I use my laws of logarithms, which I'll talk about more in a little bit, this will be ln of k plus ln of x, okay? And what happens to this guy if I take the derivative of this whole thing? Okay, if I take the derivative of this whole thing, then if I take the derivative of ln of kx, the derivative of this is 0, and the derivative of this is 1 over x. Okay, so that's why you end up with this is 1 over x. It looks just like the derivative of ln of x. Okay? All right. The derivative of the natural log of 1 minus 3x. Okay? Now this is my f of x here, so I'm going to go 1 over f of x, right? To take the derivative, I do 1 over the inside times the derivative of the inside. That's my chain rule. And I end up with minus 3 over 1 minus 3x. Okay? Here we have another example, y equals x cubed times the natural log of x. I have one function here and another function here, so I'm going to use my product rule. Okay, I have this situation, and so I take the derivative of the first one times the original second one plus the derivative of the second one times the original first one. And I end up with that expression. I simplify. Okay, this term simplifies to x squared, and there's x squared in each of these terms here, so I can factor out the x squared, and I end up with this. All right. Now let's talk a little bit more about laws of logarithms. How are they going to be useful? Well, what are the laws of logarithms first? First of all, ln of AB is ln of A plus ln of B. ln of A over B is ln of the numerator minus the natural log of the denominator. And here we have the power, I think that's called the power, I don't remember exactly, but the natural log of A to the x equals that derivative, that power comes out to the front, and I end up with x times ln of A. Okay? Let's see how we can apply these to certain situations. Differentiate with respect to x this function. Okay, so if we were to use the same method that we did before in the previous examples, we would still get the right answer, but it would just take a lot longer, and I'll show you why. Okay, if I have this, I have the natural log of this function, but I have inside this function a product. Okay, so since I have a product here, that means this part, when I derive this part, it's going to get pretty long, and that's what happens over here. Okay, this becomes 1 over x e to the minus x, because that's the inside stays the same, times the derivative of the inside, which is this whole thing. And so I end up with this function, okay, and you can see that it gets kind of long. It gets up to here, okay? There's a lot more room for error. But if I use my laws of logarithms, and since I know that this is, if I treat this like a and b, okay, in this example, I use this rule here, I can split up this into 2 logs, the sum of 2 logs, right? And so I end up with the natural log of x plus the natural log of b, or e to the minus x. Okay? And so now this becomes a little bit simpler to work with because now I have 2 terms which are a lot simpler. Okay? So I have natural log of x plus, and this simplifies, I can bring that down to the front, and I end up with minus x ln of e. Okay? And what's ln of e? The natural log base e of e is just smiley face 1. Okay? They cancel each other out, and it just becomes 1, right? Okay? So this becomes natural log of x minus x. This is way easier to derive than this function. Okay? And notice that I have the same answer here. So just be aware of this. If I can split it up into 2 terms, a log into two separate logs, the sum of 2 separate logs, then try to do that because it'll make your inside a little bit easier to work with. Okay, here's another example. This time I have a product on the bottom and a quotient inside my log. Okay? So I end up with the natural log of x squared minus the bottom, right, which is x plus 2 times x minus 3. This can be split up even further, and notice the extra parentheses here, so I'm being careful with this minus sign. This is the sum of 2 logs, so I end up with the natural log of x plus 2 plus the natural log of x minus 3. This 2 in the x on the x squared in the power goes down to the front, and so I end up with 2 ln of x minus ln of x plus 2 minus ln of x minus 3. And now it's a lot easier to derive, isn't it? Okay, so I take the derivative of this and this and this. Okay, and since this is just a 1x, that becomes a nice just 1. Okay, the derivative of that becomes 1. Same thing here, and then I end up with my final answer here. Okay, now just remember. Okay, I mentioned it briefly at the beginning of this video. A derivative is valid at most only on the domain of the original function. So since the natural log of x has a domain of x is greater than 0, whatever the derivative is, that also has at most this derivative, okay, is valid at most on this domain. Sometimes it's not even going to be valid on the entire domain, but we can just say at most that it's valid there. So just keep that in mind. Don't try to use this function for negative numbers, okay? Don't say, oh, well, that must mean that when x is negative 2, this is going to have a derivative of negative 1/2. Okay, that won't work because that's outside our domain. So these functions here even would only be valid on the domain of this function, where this inside part has to be greater than 0. Okay? So I could figure out the domain of this to be able to apply that to the derivative. Okay?